let's talk about solubility product. So, in the case of equilibrium where you're dissolving a solid that isn't going to dissolve all the way. So, it's also called KSP, so for K, the equilibrium constant of the solubility product. And basically it's where you put some kind of solid in some water, usually, and by equilibrium, some of it's dissolved, but not all of it. And so that what we say is that that solution is saturated with respect to the solid, whatever the solid happens to be, whether the solid is NaCl, table salt, or with respect to the pyrite. Now, one thing that I think is really interesting about an equilibrium condition is that if you followed one little sodium atom around in an NaCl saturated solution, that sodium atom would sometimes be in the solid, sometimes it would be in the aqueous phase, sometimes it would be in the solid, and it would just go back and forth. But on average, the concentration in the solution of both sodium and chloride would be the same at different times when it's in equilibrium. So let's talk maybe about lead carbonate. So lead carbonate is a solid that's going to dissolve to form lead 2+ and carbonate oxyanion in solution. And the KSP for that is basically the equilibrium constant, which is lead 2+ times, or the concentrate, which is the concentration of lead times the concentration of carbonate. And usually it's the equilibrium constant is products over reactants, but in this case the reactant is a solid, and so as you remember, solids and liquids do not participate. Solids do not participate in the equilibrium expression, and so the concentration of lead 2+ times the concentration of carbonate in solution are going to equal a specific number, which is the KSP. And in this case, it's 7.4 times 10 to the negative 14th. But there's a whole variety of equilibrium constants, and they're tabulated in the back of most analytical chemistry books. You can have lead carbonate like we saw on the last page. We can have NaCl like we saw for the demonstration, where you can get 360 grams of sodium chloride in a liter of water to dissolve, but more than that would not be able to dissolve, and so you would have an equilibrium developing when the solution was saturated with respect to the NaCl. You can also have something that's a little bit more complex. Is something that does not have a one-to-one stoichiometry like these two cases here. So if you have yttrium carbonate dissolving, then you're going to have 2 yttrium 3+ in solution and 3 carbonate 2- in solution. And so the KSP is going to be yttrium 3+, the concentration of yttrium squared times the concentration of carbonate cubed. And that's equal to 1.03 times 10 to the negative 31. So how can we calculate if we know that if we know that we put some yttrium carbonate into a beaker of water? How can we predict what the final concentration will be when it's in equilibrium with the solution? Well, let's check that out. So basically, we can write the equilibrium expression, and then we can write we can write the reaction, the dissolution reaction, and then we can write the equilibrium expression, just like we saw on the last board. And then let's set X to the amount of this yttrium carbonate that's going to dissolve. And you'll see why it's important to really define what X is in a second. So now we can write the KSP, where KSP is equal to 2x squared for the concentration of yttrium squared. It's going to be twice because there's 2 yttrium that dissolve from each molecule of yttrium carbonate that dissolves. Or there'll be 2 yttriums in solution for every yttrium carbonate molecule that dissolves. So you have 2x squared times 3x cubed, which is the concentration of carbonate in solution, cubed for every yttrium carbonate that dissolves. So we multiply that out. We have 4x squared times 27x cubed, and then we continue to multiply that out, and we end up with 108x to the 5th. And that's still equal to the KSP. And so we can solve for x in this equation and come up with a number for x, right? But now we don't care about really what x is. What we care about is what is the concentration of yttrium and what is the concentration of carbonate. And so the concentration of yttrium is going to be 2x, so we can calculate that out, and the concentration of carbonate in solution is going to be 3. The more common ion, or anion in this case, we're going to say oxalate, that you have in solution, the less soluble things will be. So let's take, for example, and that's called the common ion effect. So let's take, for example, the cadmium oxalate. So cadmium oxalate dissolves into cadmium 2 plus and oxalate. So we have a KSP for that. And so the first thing, let's just predict the concentration of cadmium 2 plus in solution if we have excess cadmium oxalate as a solid. So the KSP is 9 times 10 to the negative 8th, and we'll just say that the concentration of cadmium and the concentration of oxalate, we just started by putting it in water, so those are the same, so we'll define that as x. And so it'll be x squared, so we solve for x easily, and we end up with 3 times 10 to the negative 4 molar. Is the concentration of cadmium 2 plus in solution. But what if we started with a solution that already had some oxalate in it? So say 0.05 molar oxalate was already present in the solution when we added the cadmium oxalate. Well, so then we have a slightly different KSP expression. The KSP value is still the same, but the concentration of cadmium is going to be x again, and then the concentration of oxalate is going to be 0.05 molar plus x for the added oxalate that will join the solution as each cadmium oxalate ion dissolves. So then we can likewise say x squared, we can likewise solve this equation for x using the quadratic equation. And say that x equals 1 times 10 to the negative, or 1.8 times 10 to the negative 6 molar, and that's the concentration of cadmium 2 plus in solution. And so when you compare these numbers, you can see that because we had a bunch of oxalate already in solution when we added the cadmium oxalate, we have much less cadmium, much less of it dissolves, and therefore we have less cadmium oxalate, or less cadmium in solution as a result of starting with some concentration of the common ion. Why do we care? Well, we didn't always have so much fantastic instrumentation, and so separation by precipitation was actually very common. And I think you guys do a lab of that in the general chemistry curriculum. So basically, one of the neat things that you can do is is to separate things based on precipitation. So if you had a mixture, we can look at the KSPs for some sulfate salts. So barium sulfate, calcium sulfate, and lead sulfate have pretty different KSPs, times 10 to the negative 10, times 10 to the negative 5, and times 10 to the negative 8th. So it would be possible, if you started with a mixture, a beaker with a mixture of lead, calcium, and barium in it, and you added a little bit of sulfate, the first thing that's going to start to precipitate is a barium sulfate. So you're going to precipitate a good portion of that barium sulfate, and you can calculate exactly how much, but we're not going to do that. You can precipitate a good portion of the barium before any of the lead, which it will precipitate next, before any of the lead will precipitate. And then so you can precipitate barium sulfate, and then if you add a little more sulfate, you're going to end up with barium sulfate and lead sulfate as a solid, and just calcium and sulfate, or calcium in solution. There's also such thing as complex formation, and so this is when you have a high concentration of the common ion, the oxyanion, or I'm sorry, the anion in solution. It could be the cation too, but basically it's when you have high concentrations of one of the things that this is going to dissolve into in solution already. And so the KSP is predicting the concentration of the free ion in solution, which sort of starts to break down when you have a lot of one of the common ions in the solution already. So we'll talk about lead iodide. So we have lead 2 plus 2 I minus. We have a KSP of 7.8 times 10 to the negative 9. I'm sorry, 7.9 times 10 to the negative 9. So if you had a bunch of iodine in solution already, then for every the lead plus can react with that iodide and form lead iodide, or lead with 1 iodine, lead with 2 iodines aqueous. You can have lead with 3 iodines, lead with 4 iodines, and so there will be more lead that dissolve, or more of this lead iodide will dissolve than what you would predict with the KSP, because some of the lead is getting slurped up into these other complex because you have complex formation, and so some of the lead is getting slurped up by these complexes, and those are governed by additional KSP values. But you can write all these expressions, but they all have to be simultaneously satisfied. So you have your K values over here, but the concentration of lead, since this is all taking place in the same beaker, the concentration of lead in the solution is exactly is one value. You can't have a different concentration of lead here as here, because it's all happening in the same beaker. Of course, in reality, in realistic systems, this is all a bit more complex. Let's take, for example, mercury chloride, where you have mercury chloride dissolving, or in saturated solution of mercury chloride. Well, some of that mercury is actually going to hydrolyze with water and form a hydroxide, a mercury hydroxide. Some of it could disproportionate from mercury 2 plus to mercury 2 plus and mercury liquid. Some of it can form an ion pair and have the solid dissolve into an aqueous form, a liquid form. You could also have adsorption and coprecipitation occurring when you're doing. So those are things to watch out for in these in the experiments, but also kind of gives you a flavor of how complex these experiments can be. And so when you're using KSP values, you really want to be careful, because the KSPs that are reported depend on the conditions under which they were measured. So what are the experimental parameters, what are the physical conditions, the temperature, the pH, of course, what technique was used, and what kind of ionic composition